Hi everyone. My name is Abdellatif Khlifi. I am a senior software engineer from ARM, and thank you for having me here. On behalf of my team, I'm pleased to showcase the Corstone-1000 platform. Corstone-1000 is a secure IoT system on chip. It's certified and uses the Yocto project. Today, we'll have a look at the software stack of the Corstone-1000, and we see how Yocto is used to design our software stack, some quick steps to get the code, build it, and run it. Then later, we can go for a Q&A session after the presentation. So Corstone-1000 is a SoC bringing the Cortex-A and M cores together into one chip for IoT. So joining performance and real-time response and efficiency. The M core, which we can see in the middle of the diagram, is the secure enclave and the root of trust. It is the Cortex-M0+. The A core is dedicated for non-trusted applications connected to the internet, and it's the core on the left, the Cortex-A35. The software stack is 100% open source, and we are using different projects like Linux, U-Boot, Trusted Firmware A&M, Opti, MCU Boot, RTX RTOS. Our software stack is certified PSA level 2 and SystemReady IR. These cores are running in parallel, and later on we'll have a look at how they are interacting. So the main features of our software stack is focused on security and flexibility about running different distros. So the features are involving secure boot, which involves signing and verifying different images while they are loaded, and by referring to one root of trust, the secure enclave, which will verify all the images before being executed. We also support PSA secure services, and we are meeting PSA level 2 ready requirements, and this involves the API allowing the communication between secure enclave and the A core, between the secure side and the less secure side. As stated earlier, signing images and verifying them, they are all done through the root of trust, the secure enclave. We also support UEFI services in U-Boot, meeting SystemReady IR, and we tested different distros like Debian and OpenSUSE. We support OTA as well through capsule updates. And all this, it's open source and supports Yocto and Linux. Regarding the Yocto support, our software stack is using MetaARM, which is hosted in yoctoproject.org and maintained by John Mason and Ross Burton. We have two machines for Corstone-1000. We have the AVP machine, which is the hardware emulation, and it's used to for a quick time to market for developers who want to use Corstone-1000. They can download AVP and design their software there while the hardware team is working on the hardware. So we have a different machine as well, which is MPS3 machine, FPGA board. And we are using Poki-Tiny distribution to generate tiny images because Corstone-1000 has tight memory constraints, and we need small images. We created two images, Corstone-1000 image and Corstone-1000 init image. The first one is the main image. It generates the WIC file, and this file is written to the flash and contains all the binaries and also signs the different images. regarding the second image in InitRAM-FS1, its purpose is to generate the file system, the Linux file system, where we host different test applications. And as a reference, the InitRAM-FS bundle, which is the kernel and the file system, they are around 5 megabytes only. Yeah. Next slide. So we would like to state that we like many features in Yocto. So we like how Yocto allows us to organize our software stack into different layers. So it's very helpful regarding the software architecture, how to implement our software architecture in a modular way. We like as well how common features is isolated into different classes or through ink files. So we can put these common features in these specific files and share it between platforms. We also use machine overrides to enable specific settings for the Corstone-1000 without impacting other platforms. We also like how dependencies are handled in Yocto, task dependencies or recipes dependencies. So it's easy to fine-tune and tailor the distribution and to set specific dependencies we need. So this was very helpful regarding signing images and using specific recipes to do that and configure Yocto to run the signing at specific stage of the build. We also like the wide range of the open source packages support in Yocto, which is very helpful. We like, of course, the very active and helpful community, Yocto community, and that Pokey and Open Embedded are actively maintained as well. So this is very helpful and speeds up the development time. One thing that we hope it could be improved is about the Rust native compilation. It takes a while, and we hope that in the future this could be addressed. So regarding how to build the software stack, so it's really quick and easy. We need only 2 commands to do that. So we need to clone the software stack from MetaArm. We use a specific tag. So we have different software releases and each one is tagged. So this is the latest one. It has been recently released. Second step is to run the cas command to build the software stack. By the way, cas is very helpful. It parses YAML files. It checks out Pokey and Open Embedded Core and checks out the version that we specified in the YAML file, and then generates the BB layers and the local.conf. And all this is done in the background. The final binaries generated, there are 2 binaries. BL1, it is the secure enclave ROM binary. And the second one is the WIC file, which contains all the remaining binaries, which will be copied to the external flash. Regarding running the software stack, it only needs 1 command, so which is the following. And this command will automatically download as well the FVP. So it will download the FVP from the cloud and it will install it in the Yocto environment, and then it will run the software. When we run that command, we will see these terminals. So, and this terminal will show up while the Corstone software stack is booting. So first we will see the one on the top left, the secure enclave, and it is the M0 Plus core. We'll see the logs from MCU boot and the TFM, and at certain stage, the M0 Plus, the secure enclave, we release out of reset the A core, the Cortex-A35. Then you will see the OptiOS logs on the top right, and that's the secure side of the host. And at some point, we see the other terminal, which is the embedded Linux terminal, which is running at the ICO non-secure side. And after Linux finishes booting and you get access to the prompt, we can run the external system on demand when needed. And to do this, we use a command, and we give it parameters depending on the kind of test. And when we do that, the external system core will be released out of reset, and then we will see the logs from external system. The same behavior, these logs and this concept, it's also applicable to the FPGA board. So the same thing happens with the FPGA board. If you are interested for extra details and resources about Corstone-1000, please refer to these resources, and also please get in touch if you are interested. We are happy to help.